Hello everyone. In today's video I will discuss about dynamics of rotation. Until now our discussion was centered on dynamics of one particle, but in this chapter we will consider dynamics of system of particles. System of particles can be divided into two subgroups: discrete and continuous system of particles. Discrete system of particles is formed when countable number of particles form the system. Each of particles locates at different independent locations. Figure shows n number of particles scattered in space, where n is equal to 4. While analyzing the motion of discrete system of particles, we consider each individual particle's motion. Continuous system of particles forms rigid body. A rigid body is continuous mass distribution in space which remains undeformed on application of external forces. Kinematics of rigid body rotating about a fixed axis. The particle of rigid body rotating about fixed axis executes circular motion in the planes perpendicular to the axis of rotation. The kinematic variables of these particles are defined as angular position theta, which is a vectorial quantity, the location of any particle with respect to a given coordinate system denoted in terms of angle of position vector with respect to the axis is called angular position. Angular velocity, this is also a vectorial quantity. The rate of change of angular position with respect to time is called angular velocity. Mathematically, we can write vector omega equals vector d vector theta upon dt. Angular acceleration. The rate of change of angular velocity with respect to time is called angular acceleration. To obtain angular acceleration, we can differentiate the angular velocity with respect to time, or we can twice differentiate the angular position with respect to time. So we can write vector angular acceleration, which is denoted by the symbol alpha, equals d vector omega upon dt, which again equals d2 vector theta upon dt square. If the acceleration alpha is constant, the correlation between omega theta alpha t are obtained as vector omega equals vector omega naught plus vector alpha t, vector theta equals vector omega naught t plus half vector alpha t square, vector omega scalar omega square equals omega naught square plus 2 alpha theta. These three relations are similar to what we have studied while deriving the equations for particles motion under the constant acceleration. Relation between translational and rotational variable for rigid body rotating about fixed axis. We know that arc length of circle s equals r theta. The angular position theta equals s by r, and the angular velocity is related by the equation omega equals the linear velocity v upon the radius r. The modulus of angular acceleration is related to the linear acceleration as modulus of total acceleration as alpha equals a by r. Dynamics of rigid body rotating about fixed axis. As a rigid body rotates about a fixed axis, all the particles of rigid body execute circular motion. Let's consider a small section of mass dm located at position vector r with respect to a point O of the axis of rotation lying in the plane of rotation, as shown in this figure. Dynamics of rigid body. So using the figure shown earlier, we can define torque as of force vector F applied at any point on the rigid body at vector r about the origin O in the plane of rotation as vector tau equals vector r cross vector F. The magnitude of the torque is tau equals Rf sin theta, where theta is the smaller angle between vector r and vector f. So we can write modulus of tau equals Rf sin theta, which equals r perpendicular f or Rf perpendicular, where r perpendicular is r sin theta and f perpendicular is f sin theta. Torque and angular acceleration. Torque of the force acting on any particle of the rigid body rotating about a fixed axis passing through the origin on the plane of rotation and normal to it is equal to product of moment of inertia about the axis of rotation of rigid body and the angular acceleration of the particle. So we can write vector tau equals I axis vector alpha. Let's derive this formula. Let's consider an infinitesimal mass dm of rigid body rotating about a fixed axis normal to the plane of rotation. The position of particle is vector r with respect to the origin on the plane of rotation. The force vector F is acting on this particle on the rigid body. So from Newton's second law we can write vector F equals mass of the particle, which is dm, times the acceleration of the particle, which is vector A. Torque of this force will be vector tau equals vector r cross vector F, which can also be written as dm vector r cross vector A, or which will be equal to, as we know, that vector A, which is the acceleration of the particle, which will have two acceleration components, one along the tangential direction and one along the normally outward direction. So we have the two components which can be denoted as minus omega square r in the normally outward direction and minus alpha r in tangential direction. So we write acceleration vector and we write all the terms as dm vector r vector n cap cross minus omega square r n cap minus alpha r t cap. So this will again become equal to d vector tau equals dm r square alpha k cap, because if we cross multiply, if we obtain the cross product of vector n cap and vector n cap, it will become 0, and the cross product of vector n cap and vector t cap will be in the perpendicular direction to the plane of paper. So I have denoted that direction by k cap. So we denote the term dm r square as the moment of inertia term di, where I is the moment of inertia. This is a scalar quantity, and we, as we defined, is di equals r square dm. On integration we can get the moment of inertia of entire rigid body as I equals r square dm integral. Therefore the equation of torque becomes d vector tau equals di vector alpha, or tau equals I vector alpha. Moment of inertia. Moment of inertia is the rotational inertia of rigid body about the axis of rotation. This is a scalar quantity evaluated by the formula as we derived earlier. I axis equals integral r square dm. Moment of inertia of a particle of mass m located at radius r perpendicular to the axis of rotation is evaluated as I axis equals mr square. So let's obtain the moment of inertia about this axis of entire rigid body. So we simply add the moment of inertia of every individual particles, and we obtain the formula I axis equals summation I equals 1 to n mi ri square. Now let's discuss about parallel axis theorem. Moment of inertia of rigid body about an axis at a distance d from the axis passing through its center of mass and perpendicular to the plane of rotation is the sum of moment of inertia about the axis passing through the center of mass and the quantity mass times the square of distance between the two axes. In the mathematical form we can write I axis equals I center of mass plus total mass times the distance between the two axes square. Perpendicular axis theorem. Moment of inertia of a plane lamina about an axis perpendicular to the lamina is the sum of moment of inertias about two axes perpendicular to each other in the plane of lamina such that all the three axes intersect each other at one point. So in mathematical term we can write Iz equals Ix plus Iy. Moment of inertia of a stick of mass distribution lambda per unit length about an axis passing through its center of mass and perpendicular to it. Let's choose the axis system such that center of mass is the origin, x-axis along the length of the stick and y-axis passing through the center of mass. Evaluate the moment of inertia of section of length dx located at a distance x from the origin. The moment of inertia of this section about the axis passing through the center of mass and perpendicular to it is di equals x square lambda dx, because lambda dx is the mass of the section considered and x square is distance from the axis. So moment of inertia of whole stick will be ICM equals integral minus L by 2 to L by 2 x square lambda dx, or on integration and putting the limit we get lambda LQ upon 12 which equals to ml square upon 12. The moment of inertia about an axis passing through an extreme end of the stick and perpendicular to it is evaluated using parallel axis theorem as I axis equals I center of mass plus md square. So I center of mass, as we already obtained, as lambda LQ upon 12 plus md square is lambda L square upon 4. On summing these two quantity we get lambda LQ upon 3, which is nothing but ml square upon 3. Moment of inertia of a circular ring of mass density lambda per unit length about an axis passing through center of mass and perpendicular to plane of the ring. Let's consider an arc of infinitesimal length ds. The mass of this arc will be dm equals lambda r d theta. Moment of inertia of this section will be di equals dm r square, which will be equal to lambda r d theta r square. Integrate the moment of inertia through the entire perimeter of the ring. So we put the limit from theta from 0 to 2 pi, and we get I about center of mass will be 2 pi lambda r cube, which can be written as m r square. These moment of inertia are standard moment of inertia, and we can remember these moment of inertia to solve the problems. Moment of inertia of a circular disk of radius r and mass density alpha per unit area about an axis passing through its center of mass and perpendicular to the plane of disk. Let's consider a ring of radius r and width dr. The moment of inertia of the ring will be di equals 2 pi rq alpha dr. Let's integrate this moment of inertia to obtain the moment of inertia of entire rigid body. So we integrate and we obtain I equals pi alpha r4 upon 2, which will be equal to mr square upon 2. So we remember this standard result, that the moment of inertia of circular disk about an axis passing through center of mass and perpendicular to it is mr square upon 2.